Hey you guys, this is your second installment of Chapter 10. Chapter 10, in our first video, we did sections 1 and 2. Now we're going to do sections 3 through 5. So we're going to still be discussing molecular geometry and looking at all those different shapes. And now we're going to move on to hybridization of atomic orbitals. So let's talk about Lewis dot theory and how it explains bonding, because that's really what this chapter is about, is how do things bond? Why do atoms bond with each other? So Lewis theory, remember, was about valence electrons. So if we think about Lewis theory, we think about sharing, right? We're talking about covalent compounds, and covalent compounds share electrons between atoms. So when we looked at this idea of Lewis theory, and we looked at the idea of H2 and F2 are these specific molecules, when we would draw out and think about covalent bonding, we would see something like this. And we would say, oh, here we go. Here is a covalent bond. It is a sharing between two of the atoms. Now, the bond enthalpies, if you remember from chapter 9 and just enthalpy from chapter 6, enthalpy is an energy exchange. And there's an enthalpy for the hydrogen-hydrogen bond that has a value of 436 kilojoules per mole. And it has a certain bond length associated with it. Fluorine has a lower bond enthalpy and a longer bond. And we can make sense of that because we can think about, well, it's easier to break a bond, hence this lower number, with something that's further away from each other. These F's are further away from each other. So when we were to draw the Lewis dot structure, we might say this bond is, we would draw it a little bit longer because it's further away, so it's easier to rip them apart from each other. So when we talk about how bonding occurs and we think about our atomic orbitals, we would view that bonding using valence bond theory and Lewis theory by saying there's an overlap of the atomic orbitals to create the bond between the two atoms, which create a molecule. Now, for this situation here, on fluorine, we would see, well, the two 2p orbitals would overlap from each fluorine atom. And that might be okay. And the reason it's okay to think of it that way is because these are both linear molecules. And since they're linear, if these two s orbitals overlapped, you would get something like this, and those hydrogens would be right next to each other, and that would form a linear bond. And the same thing with the p orbitals. Now, the p orbitals look a little bit different, but even so, if they did overlap one to another, you might see something like this. Say these central portions here are the fluorine atoms. You would still get a linear molecule, and linear, that's good because that's what it is. And then you could explain the bonding through this just simple overlap idea. And it would also explain the shape of the molecule. So this valence bond theory that we're talking about here, VBT, says that bonds, the theory was that bonds were formed by sharing of electrons from the overlapping atomic orbitals. See, that's the key word, atomic orbitals. An atomic orbital is the orbital of an atom alone. So we're going to see that this doesn't explain all of our observations of molecular shapes. So as far as continue on, though, with valence bond theory is this overlap idea. And when atoms get close to each other, they start to get close. And remember, in the middle of an atom, there is a nucleus, and in the nucleus, there's positive protons. But there's also electrons. So you might think of, well, there's some repulsion and then there's some attraction. Here we've got some attraction between the nuclei and the nucleus from each one, but then we might have some repulsion. But you might be able to visualize, well, maybe if I'm doing two hydrogen atoms, the protons will attract each other enough such that when they overlap and they get close enough to each other, then the electrons that are here can envision that they might be occupying a space here in between them, that they both now feel like they are helium. Remember, things share to become a noble gas, 1s2. So in valence bond theory, these things start to get closer and closer to each other. This is where attraction would be showing up here. This is attraction between these two atoms. Then when they get close enough, they might start to overlap. Even more attraction is occurring between the nuclei, and then the electrons are starting to think, well, yes, this is a good idea. I'm going to become helium. And then falls down into a lower energy well down here and just kind of sits here. And as it sits here, and the PhET animation I'm going to have you guys look at for the discussion, is that you have this type of thing where they're going closer and then further away, and then closer and further away, just kind of back and forth like that, and they sit in this well. Now, if they start to go up this side, that means they're getting too close, and then repulsion of those nuclei will occur, and they will repel each other. Now, somehow, if I tried to squish these guys together, we would get repulsion, and then when we got repulsion between the two nuclei, you would see an extreme increase in energy, and they would fly apart. So for a diatomic molecule to exist, there has to be a well here that it can exist in. We'll be using a PhET simulation for this in our discussion that looks like this. So what you do here in this discussion, and for your chosen or assigned molecule, I think I have you guys choose one here, is that over here in this area of this PhET, you can choose which diatomic molecule to look at. And when you choose it, it will pop up a potential energy diagram. And the potential energy diagram for this one is an argon-argon. The one I'm showing you now is argon-argon. And an argon-argon bond is a diatomic noble gas, which seems ridiculous, but because, you know, those noble gases don't really want to overlap with each other. But say they could, and if they could, this potential energy well here is a way to visualize how stable that diatomic molecule would be. The deeper this well, the more stable the molecule. So if you choose one like the oxygen-oxygen, the well is really deep. But if the well is really shallow, say here's your line here, if it's really shallow, that means that that molecule is unlikely to form. Now all of these numbers here, this is fun sheet number 5 that I'm asking you guys to do this analysis with. These numbers are areas of attraction or repulsion, bond creation or not, and most stable areas. So number 5 over here would be like really unstable because you're squishing them together. Number 3, if it did form a bond, would be somewhat stable. So I'll let you guys do your analysis and post your chosen molecule to the discussion board for that. So this is about valence bond theory and how valence bond theory explains bond formation. That's what fun sheet 5 is about. Now let's look at just what, this is still valence bond theory, and valence bond theory is the idea that two s orbitals overlap, this is hydrogen, and then they overlap in such a way that the electrons will occupy a certain space, and that space you might think of one being up and one being down, their spins being opposite to each other, but they're occupying a space here such that they will hold the two hydrogens together, because one hydrogen says I'm 1s2, and the other hydrogen says I'm 1s2, and that's getting that noble gas configuration, which then leads to bonding. This is valence bond theory and the idea of why bonds occur. What about ammonia? Now ammonia is NH3 up here, and ammonia, remember nitrogen has a certain electron configuration. Valence bond theory has only to do with atomic orbitals, and those atomic orbitals for ammonia you see there are the p orbitals. The p orbitals are the only ones that have any empty spaces. See them right here. So you might think, oh, hydrogens come along and they fill those empty spaces because there's 3 of them. So you can say, oh, look, they just pop into those spots and this will make the ammonia molecule. So we can envision if the bonds do form from this overlap on nitrogen, what would the molecular geometry be? Now we've already learned a little bit about molecular geometry in chapter 10, sections 1 and 2. So if you recall, if you draw ammonia's Lewis structure was like this, even if we draw it flat like this. And then we would have a lone pair here. We might say, oh, there's the Lewis structure for ammonia. Now, if this structure was created from atomic orbitals only and created, as we was shown up here, from p orbitals, these p orbitals are at 90 degrees to each other. So if you use those, those orbitals, you would predict that you would have a 90-degree angle, kind of, I guess, like this picture up here. It would just be 90-degree angles between each other. And that turns out not to be true. If you recall that those angles are based on a tetrahedral arrangement, that tetrahedral ideal angle is 109.5. Now, if you remember, that's the 109.5 is the ideal. But when there's a lone pair like this, remember from our VSEPR theory, this makes it less than 109.5. And there it is, that 107.3. So this idea of just overlapping atomic orbitals with other atomic orbitals cannot be true, because if it was true, the shape of the molecule would have 90-degree angles based upon what we know about atomic orbitals. So let's talk about hybridization. Hybridization is now a way to explain the shape that we see in ammonia and in other molecules. Hybridization is the mixing of two or more atomic orbitals to form these hybrid orbitals. Again, this is a human construct in order to explain the shape of the molecules. So how to hybridize these orbitals is that it's a mixing of at least two non-equivalent atomic orbitals, like an S and a P, and then the hybrid orbitals have very different shapes from the original. The number of hybrid orbitals is equal to the number of pure atomic orbitals used. So if I mix an S and a P, that is two atomic orbitals, that would create two sp hybrid orbitals. And then to form covalent bonds from these hybrid orbitals, it's again overlap of hybrid orbitals with atomic orbitals of attaching atoms. Or you can have overlap of hybrid orbitals with hybrid orbitals of attaching atoms. And that's what that shows right there. So in the ammonia, where we saw this type of thing, we might think, oh, the hydrogen's 1s electron was overlapping with nitrogen's hybrid orbitals, and that this lone pair right here was occupying a hybrid orbital. So let's talk more about hybrid orbitals and how we can define them and recognize them. So let's first talk about sp3. sp3 hybrid orbitals, if you combine an s orbital with three p orbitals, 1 plus 3 equals 4, and that's going to give us 4 different orbitals. Now you might think, why am I doing this? Well, I have a molecule, like I do the ammonia molecule, that has 4 groups around it, and those 4 groups need 4 orbitals. So you have 3 hydrogens and 1 lone pair, and that is 4 orbitals that are required. So when we see this hybridization, these newly shaped things, and I posted a video for you in the discussion board to get a little bit of a visualization of this, and when they come together, they will form 4 hybrid orbitals. And you notice that this is a tetrahedron here. And if you recall from our previous VSEPR idea, tetrahedron comes from tetrahedral. There's a center to this, and then there's 4 sides. I have highlighted one side on your far right, and then if I highlight the other, that's another side of the tetrahedron. And then if I highlight even another, like the bottom, and then if I highlight the back side, that would be the back side. It has 4 sides, remember, and that's where tetrahedron comes from, and tetrahedral. And there's your center. See it right there? That's where an atom would be. So in our situation, the nitrogen would be here, and then you'd have your hydrogens on each one of these areas. And then you would have the lone pair in the other area. So let's talk about carbon. We know as far as sp3 hybridization goes, there's the center of that tetrahedron. There, and this is methane, which is CH4. You can kind of envision the ground state of carbon being hybridized. The atom itself, this is carbon in the middle, being hybridized. This is the atomic orbitals and how the electrons are arranged. If we promote one of these electrons up to here and then mix them all to make this hybrid, we get what's called that sp3 hybrid orbitals. There's 4 of them, and then hydrogen can come in and bond. It's in that spot, and now you just created a molecule of methane. And the black ones are hydrogen electrons. Same thing with ammonia. We just saw that on the previous slide. Again, there's the hydrogens. And you might think about, oh, look, there are 2 electrons being overlapped in each one of these places. I asked you to do this on one of the fun sheets questions to draw a picture like this. This would be the hybridization drawing for ammonia. It shows the hybrid orbitals, which are sp3. Now, how do we know they're sp3? Because I look at the atom that I'm trying to figure out the hybridization of. I count the number of groups around it. In this situation, I have 1, 2, 3, 4 groups. Those 4 groups need 4 orbitals, and 1 plus 3 equals 4, and that's where I would get 4 orbitals in an sp3 hybridized situation. And then the bond angles. This hybridization idea predicts the correct bond angle. And remember, this is slightly deviated from the 109.5, which is tetrahedral. Now that what we just saw there was sp3. There's different hybridizations that can occur based upon the number of surrounding atoms of a central atom. So to form sp hybrids, sp would be warranted or appropriate for a situation where you have a central atom, like here, that is attached to two things, and it needs two orbitals to overlap something onto. So an example of this is beryllium chloride. Beryllium chloride, these are covalent compounds. This is a covalent compound, and you might think of the overlapping right here. But beryllium only forms two bonds. Remember, it's a reduced octet. So those two bonds are then being seen here as an overlap between the hybrid orbitals of an sp hybrid orbital. Now, the characteristic of an sp hybridized orbital is an angle of 180. And when you see that 180 and that linear shape, that means sp hybridized. Now the chlorines out here, we're not really showing all the other atomic orbitals. We don't really care as far as trying to figure out the hybridization of the central atom. These are not hybridized. And even if they were, we couldn't tell because there's nothing attached to them. You have to actually see like something attached to it and see the shape around it. These are lone pairs out here for sure. But as far as it being hybridized or having angles about it, you would think that these would be. There's three lone pairs, so you would think it'd be kind of like an sp3, but hybridized only occurs between two atoms. So it's really unsure whether or not chlorine is hybridized because it only has this one bond. And we could, with the beryllium, so we could envision just this type of thing. Now that was sp. Let's look at sp2. sp2 is 1s and 2p orbitals to make 3 orbitals. This type of situation is warranted in something that needs 3 orbitals, like boron trifluoride. So boron trifluoride is a reduced octet again, but it only needs 3. And if you recall that trigonal planar structure, this trigonal planar structure, when you have 3 things around it, is indicative of the need for 3 orbitals and sp2 hybridization. So how do you predict the hybridization of a central atom? Well, first you must need the Lewis structure, as usual, in order to figure out where the electrons are and what's bonded to what. Then you must count the number of lone pairs and the number of atoms, just like we were doing in the beryllium and the beryllium chloride and the boron trifluoride. So let's try it here. Say we have number of lone pairs and bonded atoms is 2, and you count these together. You don't separate them. It's just number of things, I like to call it. So if you have 2 things, you need 2 orbitals, and it must be sp hybridization, and that's where we saw beryllium chloride. There are 3 things. We need 3 orbitals, and that's sp2 because think of a 1 being here. 1 plus 1 is 2 for this one. 1 plus 2 is 3. 3 orbitals. And an example was boron trifluoride. If we have 4 groups around an atom, the hybridization is going to be sp3. We saw quite a few examples here. We looked at both of these. And then water also, remember, has 2 lone pairs on it and on the oxygen. So the oxygen has 4 things around it and needs 3 orbitals. So it's sp3. The nitrogen has 4 things around it and needs 3 orbitals. And the carbon here in methane has 4 things around it and needs 4 orbitals. If we have 5 things, now if you recall, our shape of 5 things around was trigonal bipyramidal. Now we need to bring in another orbital, and that new orbital will be the d orbital. And so that's why that you will see expanded octets from elements in groups 3 or below, in rows 3 or below, because they have empty d orbitals that are available to spread the electrons out in, and then you can end up with more bonds that are available to be filled. An example of that is PCl5, or phosphorus tetrapentachloride. And then we need 5 bonds, and here's 5 orbitals in this hybridized model. 6 is going to need 6 orbitals, and that's going to be octahedral arrangement, and our classic example of that is SF6. So on your fun sheet, you're going to be drawing some of these things and then identifying the hybridization of a central atom or an atom that's indicated to you. So for fun sheet question number 6, your goal is to choose one of the molecules, and I think I have assigned them to you, so please go look. I assigned you one of them, so we're not all doing the same one. And then I ask you to draw the Lewis dot structure and deduce and explain the hybridization. Now, if you look at example, not example, but table 10.4 up here, table 10.4 shows you what the hybrid orbitals look like. So if it's an sp hybridized orbital, it's linear. If it's sp2, it's trigonal planar. If it's sp3, it's tetrahedral. If it's sp3d, it's trigonal bipyramidal. And then if it's sp3d2, it's octahedral. So for example, if like on your fun sheet here, say I was going to do phosphorus trihydride. To draw the Lewis structure of that, I find that there are 5 valence electrons, and there's 1 for each of the hydrogens, so I add those together, and I get 8. The least electronegative is going to go in the middle, but since this case, hydrogen can never go in the middle, so I would draw phosphorus in the middle, and then I would put my elements around here. And once I do that, and I have a lone pair, this looks a lot like ammonia, and it makes sense because phosphorus is in the same group. This is I count the number of things, 1, 2, 3, 4 things around that phosphorus, and that means the hybridization on that phosphorus is going to turn out to be sp3. I don't worry about the hybridization of the hydrogens because they are overlapping their 1s electron with the hybrid orbitals of the phosphorus. So if I were to draw the hybrid orbitals, it would look like that. And then I would have a p in the middle, and I could draw this structure, and one of those would be occupied by a lone pair, and the other ones would be overlapping their hydrogens, and I could even put the electrons in as 1 up and 1 down, or I could just put dots. You'll see that like that as well. And then you would write a hydrogen here. I should write H, not just a circle. So that's for fun sheet number 6. So I'll see you in the discussions boards for that one. Now, as far as continuing on with double bonds, all the ones we've been looking at so far were single bonds. But what about double bonds? Double bonds form as well between carbon and nitrogen and all those things we have seen when we were drawing Lewis structures in chapter 9. So let's look about how we can hybridize carbon. Carbon can be hybridized in either sp3 fashion, and that was 4 bonds, and that was something like methane that you saw. Here's my dash wedge line structure that shows my 3-dimensionality. This was 4 bonds, and 4 bonds is very common for carbon, and that would be your sp3 hybridized carbon atom, where all the bonds are single. But we do know that carbon forms double and triple bonds. But how are those double bonds formed in this type of hybridization theory? Sp2 hybridization is where you have 3 bonds. Remember, 1 plus 2 equals 3. So if you just have carbon here, think about doing the hybridization again where you promote one of them. If I do that, then I have 3 of these that could possibly form bonds. But when we look at them as hybridized, they get renamed. Now, I kind of made a mistake there by circling that and pointing there because one of these is an unhybridized p orbital. So the combination of 1s and 2 p's creates 3 hybrid orbitals called sp2 orbitals. And then you have this one guy over here that's not hybridized. He's an electron, and electrons by themselves are unhappy. So what we could see possibly happening is that this electron might be able to form an overlap or covalent bond with an electron on a neighboring atom in the same circumstances. So this type of hybridization of carbon, where you have 1 electron in each, these green ones here are sp2 hybridized, and you see they're kind of like in a trigonal planar format here. But then there's an electron up here that is not hybridized, but is going to want to overlap with something. So let's see how that overlaps and how it's going to form double bonds of carbon. Because right now in this picture, I have a carbon that's just kind of isolated like this. It's a hybridized carbon, sp2 hybridized carbon atom. But in order for something to hybridize, it must bond with something else that is also hybridizing. So ethylene, where 2 carbon atoms that are both sp2 hybridized, is this type of compound that I was just speaking of. So here is your trigonal planar. That is both of these carbons are sp2 hybridized. They will have angles of 120. That angle of 120 is a marker for sp2 hybridization and trigonal planar structure. And then here's your hydrogens. Ethylene, by the way, looks like this, or it's also called ethene if you're a stickler for the systematic name. Here is ethene. So what I'm seeing here is that there's a double bond in between. And if you look at over here, this shows a single bond. But recall on our previous slide, each one of these carbons had an unhybridized p orbital that had an electron in it. So you might envision these two guys seeing each other and then overlapping to form a bond. And that bond could possibly be the double bond. Now the pictures here start to look a little strange, but what these pictures are trying to illustrate is the hybridization of the carbon, which form what's called sigma bonds. Sigma bonds is overlap of orbitals where the electron density is located in between the atoms. So you'll notice there in this molecule, you'll see one, 2, 3, 4, 5 sigma bonds. And then if I look up here, go up to here, you will see sigma, sigma. There's the 5 sigma bonds. Sigma bonds hold things together. Now this, and do not think that there's 2 pi bonds. These are areas in which those unhybridized electrons could be living. So I could put them here, and I could have put it down here too. But if I count all my orbitals, all my electrons up, I have to be able to remain within the number of electrons that comes in that Lewis structure. Recall that ethylene or carbon has 4 valence electrons times 2 is 8 plus 4 is 12. And if we count the number of electrons in ethylene, we will get, let me change color here, we'll get 2, 4, 6, 8, 10, 12. See, there's the 12 electrons. But some of them, 2 of them specifically, are in this pi region. And this region is above or below because p orbitals are above and below. So I could have drawn these electrons up at the top or up at the bottom, but not in both places at once. So this electron density in between is a sigma bond is between and a pi bond is above and below. So I'm going to ask you in a fun sheet question to draw pictures like this that illustrate the bonding to form double and triple bonds. Here's another view of bonding in that ethene or ethylene, and there's the pi, and I could draw some electrons up there if I wanted to illustrate that there is a pair of electrons in between the carbon atoms as well as the pair here. This is showing that the electron density in ethylene is above and below, and that so you get partial negatives here and partial positives out here, just like we saw in those bond moments that we drew on chapter 9. How about triple bonds? Triple bonds require a single bond between the carbons, but it also has a triple bond, which would be 2 extra bonds. So remember, when we do our hybridization, we go through what I only need 2 bonds to hold the atoms together. So this is happening in what's called acetylene. Acetylene looks like this. Let me draw the Lewis structure of acetylene for you up here. It looks like 2 carbon atoms together with hydrogens on either side. And if we look at C2H2, the number of valence electrons for that compound would be 10. And so if I count up those electrons, you'll see we have 2, 4, 6, 8, 10. So in order to only have 10, remember I would need triple bonds or multiple bonds, in this case triple. Now to hold them together, to hold the carbon atoms together, you need sigma bonds, and I only need 2 bonds. Now recall bond angles tell you something. So the bond angle between the carbons and the hydrogens is all 180. That 180 is linear, and that 180 means sp hybridization. So sp hybridization has only 2 of the orbitals being hybridized. so as to create two empty spaces that something could come overlap in, but then you have these two ones that are left over. And now remember, those two looks like if this is Z, 2PZ and 2PY, it looks like the 2PX were the ones that were hybridized. And then to draw those funny pictures, I mean, you might think about here are these p orbitals that are unhybridized and they have electrons in them. And then let me draw the other one. You can say, oh, here's the other one. I meant to change the color here. And then here's the other one. And they also have an electron in there to overlap. So these two behind here might form a bond when they overlap to be one of the pi bonds. And then these up top here would overlap to form 3 bonds. Where are those 3 bonds? There's one there. There's one there. And then finally, there's one there, which was the sigma bond. So when you draw those funny pictures, you'll see something like this. You see sigma bond. Here's a sigma bond in the center here holding the 2 carbons. There's a sigma between the carbons and the hydrogens. But then to form that triple bond, you have 2 pi bonds. There are 2 pi bonds here, not 4. It looks like there's 4, but there's 1, and this guy's kind of buddied up with this one here. And then there's another that's here, and that one, its counterpart is over here. So I call this the hot dog bun. Kind of looks like a hot dog bun with a hot dog in the middle. But there are not 4 bonds. There are 2 pi bonds and a sigma bond. So when I draw my picture of acetylene, here's the sigma bond, and then the pi bonds are also there. The sigma bonds are between the hydrogens on the end, creates a 180 angle between everything. That 180 speaks Sp hybridization and linear shape. And there's how the bonding looks again. You have acetylene has a lot of electrons in here, and you can think how many electrons? It's got 2, 4, 6. And sure enough, those electrons, they are negative. So you have partial negative in the middle, partial positive on the outsides here. And you might think of the bond moment pointing in this way because carbon is more electronegative than hydrogen. And sure enough, this is a kind of a reactive area. And if something positive happens by, it goes out and attacks it. And that's explains the reactivity of these molecules. Now let's keep on going. Do another example here because you guys are going to do a fun sheet question. I'm looking forward to your drawings. Describe the bonding in CH2O. Well, first, let's draw the Lewis structure. Now, how you would know how to put this together, recall the least electronegative would go in the middle. There it goes, surrounding by the other atoms. Now, it looks like I've added all the electrons in here. The question is, what is the bonding in here? Where are the sigma bonds? Where are the pi bonds? There are 3 bonded atoms and 0 lone pairs, so it must be sp2. So to figure out hybridization for whatever atom you're looking at, look at that atom, count the number of things around it, 1, 2, 3, and that is 3 things, needs 3 orbitals, and so that has to be sp2. And here would be one of those pretty drawings for showing the hybridization, the hybrid orbitals, as well as the multiple bonds. So recall that if you have a linear or situation or you have an atom where there are just 2 things around it, and those 2, they're just 2 things and there's no lone pairs on the central atom, that central atom has to be sp hybridized. If you have a central atom where there are 3 things around it, that means you need 3 orbitals and no lone pairs on this central one, and it's got to be sp2 hybridized. If you have a central atom that has 4 things around it, so you might think of it drawn like this. Now I'm not really drawing this 3-dimensionally, just showing the 4 things. There are 4 things, and that would have to be sp3 hybridized. And then if there are 5 things around the central atom, it would be sp3d hybridized. That's our 5 orbitals. And then if there's 6 things as octahedral, it'd be sp3d2 hybridization. So those are the hybridizations for whatever atom you're looking at. And I want you to notice here that this oxygen is sp2 hybridized also, as well as this carbon atom down here. And that's where you get this trigonal planar shape, and then you have a double bond between the carbon and the oxygen, 1 pi bond here. So again, with these sigma and pi bonds, a single bond is 1 sigma bond, a double bond is a sigma and a pi, and a triple is 1 sigma and 2 pi bonds. So let's do an example. How many sigma bonds and pi bonds are in this molecule? This is acetic acid. If you count, looks like I have 6 sigma bonds, and those are the ones that are in between. Wait a minute, 1, 2, 3, 4, 5, 6. But what about the next one? Plus 1 is 7. Yes, there must be 1 there also. And then there's 1 pi. For your fun sheet question number 7, the goal for that was to give you practice. So I've assigned you guys a molecule in the discussion board. For the fun sheet itself, when you turn in the fun sheet, just do the 3 that are on the fun sheet. For the fun sheet discussion, do the one that you're assigned and include that on your fun sheet as well when you turn it in. So if you were going to do one of these, you would draw how it's put together, and then you would identify the number of sigma and pi bonds, and then identify the hybridization, and then draw the hybrid orbitals. So you would be drawing something like this. And this is the example that we just did on the previous slide, and this is showing the sp2 hybrid orbitals on these, the carbon and the oxygen, and it's showing the pi bond, which is illustrated by 2 lobes like this with electrons in. I can just put electrons in. And sometimes it's nice to put electrons in here, so you can just use the dots. That shows the overlap of the electrons, and we would have an electron pair right here also. So I look forward to see what you're doing here. These were drawn, by the way, with mole view, and I'm asking you guys to use that for the discussion and the next experiment. Mole view is really handy. I just drew all those pretty quickly and then put them into your fun sheet and into the discussion so you could play around with understanding the shapes of the molecules and the hybridizations. So I'll see you in the discussion board for that one.